to our blue meter. Mine's been very heavily used and abused, and it is still in great working order after 8 years here at Furuno. The ones I had prior got equally abused for many years. I've not had one fail, but usually the common fail point is either the dial wearing out or people in hot climates leaving the battery inside of it. Here's a little tip for you. You don't need the battery in the blue meter. The battery only serves to maintain memory. If you're on a boat collecting data on here and you slide the switch up to the lock position on the right-hand side, then you can turn your meter off and disconnect it. And you can either at that point turn it on and see the values again, or go back to your shop and plug it in and get power and see the values again. The battery only holds memory. I don't care about memory. I take a lot of pictures of it with my cell phone or videos. I don't leave a battery in there anymore. I heard of other techs having it happen, and then sure enough, it happened to me. I was down in Florida. It's nice and hot. I had a cheap 9-volt battery in it, and it ruptured. And I'm very lucky it didn't ruin my $895 meter. So don't even put a battery in this thing. There's no need. Unless you want the memory to be used, don't even put a battery in here. Get rid of that risk. But back to the features. On switch position 1, there is auto search mode. It's going to scan through all 12 switches, or the 11 remaining switches, and see if there's a problem on either one of them. Are there any faults? Are there any near faults? It's going to give you a smile, a straight face, or a frown face. That's kind of a quick and dirty check. If you see a frown or a straight face, you need to investigate and see what's going on. If you see a smile, please don't stop there. Still go through your switch positions and look at them. Like I mentioned, look for fluctuating voltage. Look for values that are higher than you'd like to see on a good bus, especially a new installation. The nice thing is, if auto search finds an error, you can press these plus and minus buttons to go through each MAC or source address. The only downside is when you see this source address, it means nothing to you unless you have a program that tells you source addresses, like the N2K analyzer or the NMEA reader from ActiSense. Maretron shows the address in hex. ActiSense shows it in 10 base. So you're going to have a conversion to go from numeric to hex if you use the ActiSense program with the N2K meter. So switch position 2 tells you bus errors. You don't want bus errors. If you have this meter plugged in and you are connecting and disconnecting devices, don't be alarmed if you see a bus error pop up. But it's only going to be 1 or 2. It's not going to be a continuation of them. Just that making and breaking connection, I've seen bus errors come in. So don't be alarmed by seeing 1 bus error. Bus traffic, position 3, that's your network load. How much traffic is going on? If you are connecting and disconnecting devices, it's not uncommon to see 99.9%. When it comes on and says, hey, this is who I am, who are all of you, and everybody's talking, your bus traffic can peg. But on a normal running bus, you don't want to see it that high. On a huge bus that reaches the limitations of everything, it's not out of the realm of possibility to see a steady 80% on there. But on a small boat, it really should be down pretty low. If you do not have a heading sensor, it's probably going to be single digits. Once you add a heading sensor, they're usually good for 15 or 20%. Bus power is switch position 4. That's what kind of voltage do you have at the spot you're plugged in. That's why I say it's nice to run this meter around different spots on the boat. Don't just plug into the center and say you're done. Go put it at each end of the backbone as well. When you do a new install, test each end and test right by your power insertion point. That'll tell you if your bus should be good. If you're doing diagnostics, you're going to want to plug this meter into every device's drop cable to see where a problem may lie. Switch position 5 is your shield voltage. We covered that. Don't want to see voltage on shield. Switch position 6, common mode voltage. We get into that more in the advanced NMEA 2000 class, but to boil it down in its most basic form is it is allegedly a reading of the maximum voltage drop at any given point on the network. I'm not convinced of the legitimacy of that claim, but I am convinced that it gives you that value where it's plugged in accurately. So if you plug it in, leave it running for 10, 15, 20 minutes, that'll tell you if your common mode voltage is good, because that grows over time. And then your CAN voltage levels, switch positions 7 through 12. These tell you a lot. We're going to get into that in the next slide. There's a lot of data there. But this meter cannot measure network termination. The peak meter can. It's pretty cool. So what are we measuring on switch positions 7 through 12? This, just so you understand what you're looking at, is a simplified waveform that you would see on an oscilloscope. So here, switch position 7, it's labeled net HL differential V, and 7 has an R by it. So what you're looking at is net H and net L, the white and the blue wires. What is the differential between the two, the differential voltage, the difference between them in the recessive state, R? When nothing is talking, recessive, the bus is dormant, not dominant, but the bus is quiet, it's recessive state. Right here, switch position 7, what is the difference in value from the voltage the blue wire and the voltage the white wire are resting at? Our goal there is 0 volts. We want them to be at the same place. They're not sitting at 0 volts. The difference is 0 volts. Switch position 8 is the same differential voltage, but now we're looking at blue and white in the dominant state when they are talking. We've now opened an envelope to carry data through. Each wire is supposed to move 1 volt. The white wire should go up 1 volt. The blue wire should drop 1 volt. So if switch position 7 ideal is 0, then switch position 8, anybody want to take a guess? Everybody awake? Nobody sleepy yet?
-1.
What's that?
0.
Nope, 7 is 0. But if 8 moves 1 volt up and 1 volt down, 2, yes. In an ideal world, switch position 8 should say 2 volts. It may be a little off of that, that's normal, but 2 is what we're shooting for. Switch position 9 is net H voltage, net HV, so the white wire's voltage in the recessive state, at rest. Switch position 9. Does anybody know what voltage level we should see right here? 2.5 volts. The NMEA 2000 rests at 2.5 volts. That's why I said we're up above the noise floor. So switch position 9, the white wire at rest. If our differential voltage, number 7, is 0, then we'll also find switch position 11 should match switch position 9. Both of these should be 2.5. Switch position 10, if it moves up 1 volt, now we're looking at net L, the blue wire. Or sorry, 10 is the white wire again. 9, 10. Net H. So switch position 10 is going to be the white wire in the dominant state when it's talking. It moved up 1 volt, so that should be 3.5. And then the blue wire on position 12, the dominant state, should be 1.5. I don't know if you all got paper materials. It's handy to write those values down there. If not, there's a slide coming up that has them. So if you look at it with an oscilloscope, that's the waveform you should see. These two should overlap. The bottom at rest, you just see one line. You have your different color tracers. But 2.5 volts is where everything rests. We don't rest at 0 because 0 is trash. That's where all the noise is, all the garbage. We rest at 2.5. Dominant state is logic 0 for you programmers. Recessive state is logic 1. And again, net H, the white wire, in dominant state is 3.5 volts when it opens up. Net L, the blue wire, in the dominant state is 1.5 volts when it opens up. It goes down. The differential, this little triangle is the symbol for differential. It's 2 volts. White goes up, blue goes down, 1 volt each, 2 volts total. And your recessive state, everybody comes to rest. Net H and net L are both resting at 2.5 volts. And at that point, we have a differential of 0. This is why switch position 7 is 0, typically. Switch position 8 is 2. And then switch positions 9 and 11 are both 2.5. Switch position 10 will typically show you 3.5. And switch position 12 will show you 1.5. This is where those values are coming from. If you did not have the blue meter to just flip through and give you those numbers, you have to have an oscilloscope with 2 channels to show you these, and you have to know how to set it up to read this. Adjust your range, adjust your time. Unless you're lucky enough to have one of the oscilloscopes with the handy auto button that just kicks it off and you're good to go. So any questions on what we're looking at here and where we get those values? Usually I can put it on a big dry erase board in front of you, but
how much jitter would you consider acceptable?
A few hundredths. So we've got some live photos, or not live, some actual photos taken of what you typically see. I'm okay if you've got like 2, 3, 4 hundredths of fluctuation. If you get much over that, start looking at it, just see what's going on. You can argue though that, hey, it's in range, it's within the legal limit, so I'm not going to chase it, but I'm going to start wondering why. But that's also a good reason to test your networks when they're brand new. If you test every network you install, when it's fresh, when it's happy, you're going to know what kind of fluctuations you should see on that meter. Maybe your meter is a little looser than others, but you'll see what good networks look like. It's like using radar. If you only use radar when it's dark, foggy, or raining, you're not going to know what it looks like or what it's supposed to look like. You need to use it when things are good. Get used to it. So here's switch positions 7 and 8. Here's 7. We've got a differential of negative 0.02 volts. So the blue is actually sitting higher than the white wire. It's okay. That's well within range. The dominant state where it's opened up, we're at 2.06. So it's a little wider than 2 volts. Again, that's fine. A little leeway.
Do you document this so you go back on that boat in 6 months or a year, you have a baseline?
I do.
If you take a boat owner, or do you keep it?
I keep it for my records.
Okay.
I'm a little different. Just because I'm a factory representative, usually if I'm involved, there's already been a lot of people to the boat. So I tend to hold on to my records. If the customer requests them, I'll absolutely share them. But as a dealer, I always left documentation on that stuff on board. I'd keep a little file for them. I would just scan all my reports, print them out, put it in the file, and leave it on the boat. I treated 18-foot Chris Pratt or Carolina skiff the same way I treated a 64 Viking Princess. They got the same amount of documentation from me.
Mhm.
Might have been a little thicker file, but it's the same
Yep.
stuff in it.
Very good.
So if you're good with an O-scope, this is what you're going to look at. You're going to sample a small section in time so you can see it better. Here's a nice clean waveform, nice square. You can see that we're a little open. They're recessive differential. It's going to be a little bit there. You're going to have a little bit of a positive value, but that's fine. It's within the limits. We can see here, if we look at our white wire during dominant, 3.42 volts. So here are half one, half two, 3. Maybe not. I'm not sure where they've got the scale set because I can't see the numbers. But channel 1, 3.14 volts. This might have been a photo taken at a different time because that doesn't match 3.42. But this does that for you. It gets the two different readings and calculates the difference. It calculates the difference between dominant and the overlap. The blue meter makes it quick and easy. Again, recessive at rest, the white wire, 2.4 volts, that's okay. It's within range. It's a little low, but it's in range. As long as it's stable, I'm not concerned. 3.42 when the white wire jumps up. So it's opening 1.02 volts. That's fine. That is very close to 1 volt. Speaking of doing the tests and documenting everything, on the advanced NMEA 2000, we give you a checklist sheet. I don't know if the 0400 has that sheet or not, but I know we give you the test sheet to go through and document everything. That is a great sheet to copy and keep in your toolbox for checking the boats when you get on board or when you finish an installation. Looking at the blue wire, looking at it in the recessive state, 2.4 volts, and then opening up to the dominant state, 1.36. So again, that's only 1.04 volts that it opens. That's great. Just a hair bigger than normal. No problem there. No, I'm sorry. It's a hair less than normal. It opened up 0.94 volts. It's close enough to 1 volt. Looking at 11 and 12. Again, the R, just think of it at rest. And then D, dominant, delivering data, if you will. You're opening that envelope to carry a message. Switch 4, 5, and 6, your bus power, 12.9 volts. Your shield, your common mode voltage, 1/4 volt, happy with that. If you notice in here, they got the battery image with the line. That means whoever took these photos also disconnected their battery from the meter. Bus errors and bus traffic. Play with this meter. So 7 through 12, that gives you the value for the whole network. Bus traffic and bus errors, you can go through and see each device. So if you get bus errors, you can press this play button. You can see errors per second or cumulative errors. If you start pressing the plus and minus, you can go through each device and see who is putting out bus errors. Here's a good one. This is bad news. However, look at your blue meter. Their recessive white wire voltage still was within range of what is allowed. Their dominant, it was getting up high enough, 3.24 volts, but look at that blue wire. That thing is tanked. Something is wrong. There's our blue readings. Again, everything's smiling. It's within range. And if I remember this story right, the bus was mostly working still. This occurred due to a bad transceiver. And the way they made the transceiver bad was pumping AC voltage into it until it started to die. That's the trick. To make something that you can troubleshoot with, you got to get it to begin to die, not completely die. But this is what I mean. NMEA 2000 is very robust. If you build it properly, it can take a lot of punishment and still mostly function. Common mode voltage. There's a question about common mode voltage and what you're measuring between. So shield voltage, switch position 5, is what is measured between black and shield under power. Common mode voltage, I'm going to refer everybody to read the Maretron N2K meter owner's manual on that. I will say the owner's manual for the Maretron N2K meter, whoever wrote that should be in charge of writing everyone's manuals. It is a beautifully written manual. It is not too techy. It's techy enough that it explains everything properly. And it tells you what to look for if you see a fault on whatever switch position, what wires you should look at, what could be happening. Could it be a device? Could it be the wiring? Could it be power? And it tells you what each thing does. So if you have one and you've never looked at the manual, check it out. Somebody asked if you get one, make sure the manual is included. I had a manual that was included and I wore it out. It is available for download from Maretron for free. So even if you don't have a blue meter yet, it's pretty cool to download that manual. You can learn a little bit more about CAN bus than what we even teach here today. And it's not bad. Might be something you want to read on a 1-hour plane ride somewhere.